Selective laser sintering, so laser means there's laser involved. It's doing our fusing. Selective means it's only doing certain parts. And sintering means that we're taking a nylon powder and we're hitting that with the laser, and that's sintering it and it's turning it into a solid.
Derek, so when most people think about plastic 3D printing, they're pretty familiar with FFF or FDM machines, you know, the home kind of scale, hot glue gun, laying down the layers and building up the model. There's a lot of 3D printing going on here. None of those machines in sight. Can we talk about what these machines are, how the technology differs, and then we'll move into kind of the advantages and the whole process really?
Yeah, certainly. So this is SLS or selective laser sintering technology. These particular machines, this is a 6100 by 3D Systems. In essence, what that means, selective laser sintering, so laser means there's laser involved. It's doing our fusing. Selective means it's only doing certain parts.
Yep.
And sintering means that we're taking a nylon powder and we're hitting that with the laser, and that's sintering it and it's turning it into a solid. Yeah, so it's doing it similar to the other technologies, layer by layer. That's all the same. We're literally drawing a cross section with the laser.
That's the selective part.
That's the selective part, and then it drops down, it puts another layer of powder, does the next cross section, and just repeats over and over again.
So powder bed fusion, this is what that technology is. And
Correct.
that's used in a whole lot of different 3D printing additive manufacturing technologies in different respects, I guess?
Yes, it is. Yeah, and it gets used a whole lot of different industries. It gets used for not only prototyping, which is where the technologies come from originally, but now it's definitely crossing over into that manufacturing space. The materials are sufficiently, mechanically strong enough to be able to do those demanding applications. Aerospace, motorsport, medical, all sorts. Yeah.
So when we talk about the materials themselves, we're still talking about plastics, thermoplastics, just like FDM?
Yep. So nylon, so more of a thermoset, but this is a PA12 nylon that we're running in here at the moment. PA12, PA11, PA6 are quite common materials in the powder side, and it doesn't matter whether it's 3D Systems or HP or whatever. It's all a nylon family somewhere. You can get into the TPUs and some of the more flexible materials as well. And then into some glass fields and some composite reinforced type materials as well for real high-end applications and high temperature, high strength, high stiffness as well.
So when we talk about those, the properties of the materials and kind of, I guess, temperature ratings and resilience, nylon's obviously like a kind of go-to step up for people doing FDM stuff at home. Same idea here, and then obviously further up when we're not so worried about nozzle temperatures, this machine is capable of printing things with much higher melting temperatures.
Yeah, absolutely. So at the moment we've got about 180 degrees in here.
Okay.
And that's sort of where, and then the laser's just tipping it over the edge and melting it. But it means that the PA12 bog standard's got about a 90-degree heat deflection on it, which is pretty useful for most applications. Resistant to most hot water applications because we're not normally right at boiling. And then some of the higher materials can get us up to 180 degrees heat deflection and even some flame retardants, and you're getting quite specialist applications.
So even an engine bay and motorsport applications, and possibly even forced induction at that case, like 180 degrees is probably going to be pretty good.
It's going to do most things, yeah, absolutely. And then you're also getting into some fluid resistance and oil, fuel, et cetera.
Yeah.
So there's a lot of different materials available for those different applications, but even just fluid reservoirs and all those sorts of applications. There's ways to go there too.
Cool. And it's obviously not all down to the material itself, but the actual benefits that the process provides. We often hear of, traditional FDM 3D printing, layer-to-layer adhesion issues, and those layers, we can see them stepping up on the part.
Yep.
Not so much the case of a part like this. Do you still have any layer-to-layer adhesion problems?
No, we're pretty much, when I say pretty much, a couple of percentage off fully isotropic properties. Okay. So XYZ has the same mechanical value. And then as far as the layering doesn't really tend to show up on this. We're still running at 100 micron layer thickness. Okay. But the surface comes out with just almost like a sand texture, like a sand cast texture. Yeah. We've got post-processing ways that we can improve that if we choose to. But it's the biggest benefit of this technology is the lack of support structures, which is what most people are used to when they're using printing.
Yeah.
But then powder bed, we're just fully encased by powder. And it just makes the whole process so much easier, and it gives you geometries that you probably couldn't do other ways as well.
Yeah, so let's dive into that a little bit more. I guess if you've got your print chamber, you can just stack parts up in there and fill the whole print chamber because the supports It's just supported by the powder, correct?
Dead right. And so the beauty of us as a bureau, our week looks like orders coming in from all sorts of different customers. We just lump all those together in one build. As long as we've got about a 3mm gap between them, we're pretty happy. There's some other considerations on thermal mass, and it might be a little bit of curling because it is a thermal process. But as long as we've got those gaps and we don't interlock parts accidentally, that's a wee trap that you have parts inside parts accidentally. We're human, it happens, but that's the beauty. We just pack that 3D space as efficiently as we can, and then submit the build. So you'll have 15, 20 different customers all in one build. It's a dream from a workflow point of view. Yeah,
so manufacturing efficiency and lowering the price of it is obviously great there, but you talked a bit about the design flexibility before and allowing for certain features in the design that wouldn't be possible if you had to have support material. Could you maybe talk to what some of those might be?
Yeah, so it's normally comes down to how would you normally remove those support structures, and that's internal geometries, internal cavities, and things like that. So if you physically can't get in to remove the support structure and you need to have it out, and if you think about things like double-walled ductings or things like that, we've done a lot for aerospace type applications. They're very good at making sure that things are as lightweight as possible, as thin as possible, but they put as much geometry in as possible. So if you can have all these internal geometries, but all you need to do is just blow the powder out rather than physically have to try to pick something out, it's a big advantage, and it just opens up those design possibilities.
Let's move from that and just talk a little bit about the process. Essentially, you're taking a CAD model, I assume, loading it into a slicer of sorts, and then feeding that to the machine. Can you talk us through that process?
Yeah, absolutely. So the input file is expanding. It used to be STL was it. Now our preference is a step file, because it means that faceting isn't there in the first place. And just as a wee note that most people, when they send stuff to a bureau, let us convert the file into the mesh, not yourself, because we'll do a much finer one than you will. And we still get parts come through, and you can see the faceting. That could have been a bit tidier, but does it matter? Who knows? So so we'll receive steps. I just, it doesn't really matter. We'll convert it over. We bring it into the software, just import them in. We tend to, it's always a balance between us manually orientating parts and the software suggesting orientations. And what we tend to do is if there's parts that are critical, we'll manually say that we want them at this angle, lock them in, and then let the software auto-place everything else around it. If parts aren't as critical. We've got to watch a little bit when it comes to, when you talk about design limitations. Wall thickness is one. Now the laser has a minimum that it can sort of hit, and we're down into the 0.5, 0.6mm territory. But if you've got a thin wall, 0.5, 0.6, and you tip that on its side, you've now increased that thickness, and now it will form. So there's little tricks that we can do like that as well to make the unprintable printable, if you will. So so we'll bring all those in. We'll do the 3D nest, and then again the software will take over, and then it just goes through and literally does those slices, and you can start to see this machine running at the moment. This is the cross section that it's doing right now. So that's all the software will do for us. It determines what all those cross sections look like, and then you just submit it to the machine, and away it goes.
So as long as the powder's loaded in and it's ready to go, hit play, and it does the hard work for you.
Correct.
And then after it's finished, what's the process look like from there?
So once it's finished, there's always a cooling period because it is a hot process, and if we push our luck too much and we bring parts out, the cooling process can introduce distortion. So it's priority versus patience battle sometimes. So we bring the build out. Once it's down at a manageable temperature, it's as simple as just removing the parts out. We can recycle the powder that's not used. It just comes back into the system with the introduction of a little bit of virgin material. And then we have depowdering, automatic depowdering. Basically put it in that machine, and then it just blasts. It's just, we can manually blast. Sometimes we still manually blast, but 90% of it's just done in an automatic tumbler, and it just removes the last of the powder, and we're left with a physical part.
Cool. And then in terms of post-processes on that part, what's possible? Is there anything that's always required, or is it just a case-by-case thing? 60-70%
of the parts go out just as printed with nothing special done to them. But then we're into the territory of a process called vapor smoothing, which is a chemical treatment that essentially takes, if surface roughness is peaks and troughs, it melts the peaks, flows them into the troughs, and gives you a much nicer even surface, and it also completely seals the surface. So you've got some advantages there for cleanliness when it comes to biocompatibility and what have you as well. But just makes it look better as well. But then we can also dye parts. We do a lot of dyeing. 90% of them end up black. All of our parts are white by nature, which is great because it gives us the flexibility to go any colour. Other machines might have a grey or a black as the standard, so it's a lot harder to do that with, but we're lucky that we've got the white. So dyeing's an option. Epoxy coating we do. If people need really sealed sort of parts, or if they want a bit more reinforcement. Automotive paint, that gets done a fair bit as well. But
at the end of the day, it's a plastic, right? So the same process as you could paint a plastic bumper with. Same thing here, basically.
It's just what level do you need that surface finish at? That's the only question.
I think one of the other common processes that people do with, plastic 3D printed parts is adding like heat set inserts. Is that something you do with something like this?
Yeah, absolutely. So you can go, you can either just bond it in with epoxy or something, or do a heat process and actually melt it in. You can do either of those as well.
So that would be great for creating more structural fixtures, I guess, in there. But with the detail or the resolution this can print down to, do you sometimes print like a thread into a part?
We do, absolutely. If we're getting down into M3, M4 territory, we don't. But we'll put the pilot there so it can be done afterwards. So at least you've got a centre. If we're up even a M6, I'll print an M6, but I'll always chase it with a tap.
Tidy it up a little bit.
Definitely.
So in terms of the speed of printing the part, obviously that comes into things like we talked about before with the supports and being able to print a whole chamber of parts stacked up. But how would printing, a single part in a machine like this, say 100mm by 100mm, compare to something like FDM, for example?
So on a apples to apples comparison, one part versus one part, it's probably going to be a very similar sort of a thing. We're going, say, in 100 micron layer thicknesses. For us to do a full chamber, now the height of this chamber is 460 millimeters. Typically that's going to be about 48 hours of print time. Where things start to go apples to oranges is we've now got 200 parts in here. So as opposed to one part. So the poor old FDM machine's still doing that one part. We've now just done 200 for the same time. So if you can load it up, it's actually really fast. And when we get into some production parts where we might be doing 1,000 parts or 2,000 parts for a customer per part, we're knocking things out pretty quickly. So it's the classic balance between when do you tool up, when do you print, and it's quite a blurry grey area in between.
But you'd say that this technology is definitely catching up to something like a more traditional injection moulding approach.
Catching up, but definitely will never replace. You just can't beat injection moulding for mass production, but it's that area in between, and I think, personally, 1,000 parts to 2,000, that's sort of, unless you've got some very specific geometry requirements that injection moulding can't do, that's sort of where this sits quite nicely.
And then obviously, like the lower end of that low volume stuff, prototyping, additives, still obviously got great advantages there.
Oh, massive. Even from a prototyping point of view, absolutely it does. From we call it digital inventory, but when you're manufacturing with it, the ability to change the design each time is massive. So there's nothing worse within my background is product design. I've designed injection moulding parts and what have you. There's nothing worse than you wish you could make a change, but you're now committed to a tool, right? With this, you can have a tweak every time if you wanted, and you might get feedback from the customer, from the market, whatever. Just want to tweak this, change that. There's a tolerance, whatever it is. And it just gives you that freedom. Which
change the CAD model rather than machine it all or weld it up to machine it or messy stuff like that.
100%,
cool. All right, will we be able to have a quick look in the machine? And
absolutely, So this has got a finished build in it at the moment. So this has gone right down to a full cool down process, so everything's safe to touch. So when we open this up, so immediately what you're going to see is quite a heavy door here. So this runs a vacuum. It runs in an inert atmosphere. It's got its own nitrogen generator on here as well, so there's no oxygen present during the print. And when we look in here, we've got a laser window at the top. We've got surface heaters in the down position at the moment, and then we've got the finished build down here. So essentially what's happening is our lasers sitting horizontally up here. Up in the head, we've got a couple of mirrors. And so the laser's hitting the mirrors, and it's actually the mirrors that are directing the laser down onto the top of the print.
So it's not doing the whole cross section at once. It's drawing it out.
It's physically almost vectoring the cross section. Yeah. And normally it's an outline and then an infill of some description, an infill panel. But it's similar. That's more like FDM type concept there. Yeah. So you can see in here though, this is the fine unsintered powder. Yeah. But in there is some solid parts as well. So and then the surface heaters here just for keeping the top of that print. They just flick up out of the road.
So the build platform is under here, and that's essentially dropping down each time it builds up a layer.
Correct.
And then more powder is just coated over the top?
Yeah, absolutely. So I can pull this out manually without doing any harm. So again, this is our roller here, and there's a hopper system, and this is connected over to another material system, which the powder transfers into it. So every time it dumps powder down, this just simply comes across and just you can sort of see that happening. Screeds that off and gets you ready. And correct, there's a piston under here that just keeps dropping down into the machine, big lead screw on the bottom of it. So
I think at the same time, because we mentioned powder bed fusion before, which this process obviously is, some people are going to be thinking about metal 3D printing as well.
Yep.
Works via a very similar method for SLM.
Yep.
What are the kind of differences that we're typically seeing here?
Practically very little. Yeah. You're essentially the same concept, laser, top of the surface, screeds it across, or a recoater as they call it in metal. Yeah. A different powder delivery system. In metal, normally there's a hopper or something and it's sort of coming up and pushing it across. But in essence, you're talking about this very, very similar. Probably the biggest difference is because we're completely support free here, and the parts are just floating in powder. With metal, we still have support structures because there's just more internal tension and stress in the parts, and so they need to be anchored to quite a hefty build plate. Yeah. And if there's overhangs, then they need extra support as well. So that's the main difference.
And at the end, it needs to be cut off the build plate,
correct?
Right?
Yeah.
So it's essentially welding it to the build plate.
It's all it is, just glorified welding. Yep.
So on that topic, you mentioned when we opened this about inert gas that's flooded in here as well, and that would definitely be the case for the SLM parts.
Yeah. So our metal machine, we run a argon environment. It's a little bit different than other technologies that it'll completely pull a vacuum and then run out the argon and that'll stay in there for the whole print. Others have a continual flow, and so we'll run a higher argon consumption. But either way, it's still an inert environment.
Okay, cool. Yep. And then a few people might be familiar with MJF, multi-jet fusion. Yep. Very similar to SLS, right? Powder bed fusion, is it just what's happening up the top here a little bit different?
Just a different head. So rather than having a laser, it's got a different head system. Yeah. But again, it's powder. It's exposing just certain parts, solidifying those. In the community, there's probably a bit more competition between the two, but in reality, they're pretty similar.
Yeah, and it's mostly nylon for that, which is what we're looking at here as well.
Yeah, okay, right. So that's the laser window there, and again, it's completely sealed, just so we've got that inert. Yeah. And then the laser window, that's all that's doing is just allowing the laser to come from outside the vacuum inside. But yeah, put that just to cover make sure dust doesn't get on the mirrors. So this gives a good visual of sort of the size of the chamber as well. It's pretty much. So you notice it's open at the bottom. We'll just go into the manual side of the software, piston control, and literally we're just taking it to the start position. Warning. The warning there was just saying if I hadn't taken that laser window out, there's a crash potential. Okay. So it just reminds us each time. Yeah. And then you just see it'll come, So it's quite a slow moving actuation. So that's now brought that piston right up to the starting position. And as we open this up, so we can now see that we've got that chamber completely full of the print. So now we just have to extract it. So we just slide this underneath like a knife, sealing off the bottom. So, so we take it over to the breakout station. Just put that in roughly, and that's just a temperature probe. So before we get too carried away and start getting ahead of ourselves, we can just double check what the internal temperature is and make sure we're safe. We're looking here, so 58 degrees. We're right on whether we'd take that out or not. And naturally, this will just fall apart a wee bit. Now this particular build, we've got 3 large parts, which is actually quite unusual for us. There's one big one in here. But you can see all this loose powder just goes straight back into the recycler. And that'll come in and get resifted with some virgin material, and you can see that's connected back up to the machine. You can feel a part there. There's a really large part in there, which I'll just put to that side. And then that's the immediate powder on the surface, which tends to be what we call a burnt powder. We remove that. We get the worst of the powder off on here, and the rest goes in the blaster. But roughly done. And there's a physical part. So no support structures, which the other benefit as well means that there's no contact points of that support structure as well.
No witness marks.
So the surface is nice and interrupted as well. So, so that's in there. There's another one of those in there somewhere. I'll take the loosest stuff off. Take the burnt powder off the outside. And then we've got, in this particular case, a left and a right. So this is a repair on a panel.
Okay.
So we'd 3D scan the part, and these are just some infill pieces that we've done. So they'll get bonded in and glassed in, and then that's the body repair on that particular one. So we only scanned one side, digitally mirrored, and then we've got a perfect left and right.
Awesome. Well, thanks for walking us through the entire process, and I think that's given us a lot of insight into how SLS differs from FDM and the advantages of it as well. If people want to see what you guys are doing and follow along with that, where are they best to do so?
The easiest place is actually our website, so fiadditive.co.nz. On there, we've got an online portal as well. So it's got all of our materials and processes and all that. They can go on there, they can chuck their files in there, get instant feedback on pricing, play around with different material options and machines and get that instant feedback on costs. So that's the best place.
Cool. Well, thanks for your time.
Pleasure.
Cheers.